Hi, everyone. We're going to be going over transactions part 2 today. And specifically, we're going to talk a little bit about two-phase locking and multi-granularity. So let's get started. The last lecture, we learned about serializability and conflict serializability. Specifically, remember that for schedules, we want it to essentially look like there's an ordering. When we execute transactions, no matter how we interleave things at the end of the day in the operations, to the database, it must look like there's some serial ordering of transactions, some sequential ordering of transactions. Now, checking for serializability, as we call it, is actually very difficult. And so we chose to use a smaller subset, conflict serializability, which was much more efficient and easier to check for. In this lecture, we'll be talking a little bit about how we enforce conflict serializability, and we'll introduce locking and talk about how we actually lock items. So the scheme we're going to talk about today is called two-phase locking, and this is the most common scheme for enforcing conflict serializability. This is a bit pessimistic. Like a lot of things in this course, and especially in this unit, it sets locks for fear of conflict. And so you can imagine that there's some cost here associated as a result. We might occasionally do things that may not be as efficient or as fast as we would occasionally be able to get otherwise, but that's okay because we're really just trying to be as conservative as we can, enforce conflict serializability, and set locks for essentially fear of conflicts and for avoiding. Now, there are some alternative schemes that use multiple versions of data and rather optimistically let transactions move forward. Some interesting examples of this would be optimistic concurrency control or timestamp ordered multi-version concurrency control. Things like these abort when conflicts are detected rather than trying to use a sort of scheme that would minimize conflicts. And that is not really in scope for what we're going to talk about. If you're interested, though, I strongly encourage you to look it up. They're quite interesting, but we won't really be going into that. So let's talk about two-phase locking. In two-phase locking, we're going to first have a couple of rules. Firstly, the transaction must obtain a shared lock before reading, going to denote this as an S lock, and an X lock, exclusive lock, before writing to any resource. And the transaction cannot get new locks after releasing any locks. And this is going to be one of the most important things that we cover in this unit. We'll go over why this is so important in a second, but before I do that, I want to go through the lock compatibility matrix. Observe that two transactions can have a shared lock on a resource. But if a transaction has an exclusive lock on a resource, no other transaction can have any type of lock on it. So back to two-phase locking, specifically regarding the conflict serializability part of it, two-phase locking actually guarantees conflict serializability, but it doesn't prevent the problem of cascading aborts. Let's go over first why it guarantees conflict serializability. When a committing transaction has reached the end of its acquisition phase, let's call that the lock point, at this point, it has everything that it needs locked. Any conflicting transactions either started the release phase before this point or are blocked waiting for this transaction. So if you think about it, the visibility of the actions of two conflicting transactions to the database, well, you could kind of construct an ordering of transactions according to their lock points. And the order of the lock points is going to give us an equivalent serial schedule. Now, with regards to the lock point, think about it this way. When it's reached the end of its acquisition phase, it has all of the locks it needs to do everything that is necessary. If any transaction conflicted with this, our current transaction, either it would have started the release phase before this point, meaning that it would have finished all of its work on the resources that this transaction might be operating on before we hit our lock point, meaning that the ordering we could give would be, oh, that conflicting transaction came before our current transaction, or that conflicting transaction will be waiting for this transaction and will be blocked on it. So the ordering we could give would be that said conflicting transaction would come after our current transaction. Essentially, we're able to now order transactions by lock point, which you can see is this peak in the graph when it finishes acquiring all of the locks it needs, when it has the most number of locks it'll ever hold. And by ordering transactions by that lock point, we would get a serial schedule, an equivalent one, rather. Now, two-phase locking is nice, but it's not perfect. And there's some problems here. For example, there could be the issue of cascading aborts. Let's go through an example. Here, T1 decides it's going to read A, write A. T2 decides then, after T1 writes A and T1 releases a lock on A, T2 is going to read A. So it's going to read the value that T1 writes, and then it's going to write A. And then T1 decides that it's going to abort. But now hang on a second. There's a problem because, well, T2 read a dirty value, a value that was no longer supposed to exist. Because recall, all of a transaction must happen or none of it must happen. So if T1 aborts, we need to make it look as if T1 never actually existed. None of its operations happened. But in order to do that, well, T2 read a value that directly came from T1. So then we're going to need to undo T2 as well. Not great. So here, this is called the cascading abort, where rolling back T1 would require us to roll back T2 as well. There's that dependency. So strict 2PL fixes this, and it says, let's still observe the two phases of two-phase locking, acquisition and release. But while our acquisition phase will work as normal, you just keep acquiring locks till you hit your lock point. Well, we're going to change things up a little bit. In the release point, when you release one lock, you have to release all of them. And so you can only release your locks when the transaction completes. That's when the transaction is either committed or aborted. And so these two phases in two-phase locking, acquisition, where you keep acquiring locks, and then release, where you let go of your locks, here in strict two-phase locking, become still the acquisition phase is the same. And then your release phase will basically just be all at once at the end of the transaction. That's when you say, now I'm done with working on these resources. So now I'm going to release all the locks at once because the transaction is done. The reason this is good is because then we can be sure that no transaction is going to then have to abort as a result of our transaction, such as what we had to do here, where T2 had to abort as a result of T1 aborting. Well, that wouldn't happen here because T2 wouldn't even pick up the lock until T1 committed or aborted. So it wouldn't have to be rolled back because it would never have read a value that could potentially need to get wiped. So let's go through a few examples. Here's a schedule with no two-phase locking. A is going to be 1,000, B is going to be 2,000, and we want to see what our output is. Here in our output, let's say first, T1 is going to lock X of A. Then it's going to read A. It's going to update A to subtract 50 from it, and then it's going to write A and unlock A. And for the purposes of this transaction, let's think of it like you're transacting money. So A is losing $50 here, and we're going to give those $50 to B. Okay, we're going to unlock A here. Now, T2, meanwhile, has requested A, and it's going to wait till T1 unlocks A. Then T2 is going to read A. It'll unlock A, then it'll lock B. It'll get a shared lock on B. So at this point, T2 has read the value of A as 950, 1,000 minus 50. So T2 has read the value of A as 950. Now T2 is going to get a shared lock on B, then it's going to read B. B's value is 2,000. And it's going to unlock B and print A, B, and A plus B. It'll get 2950 as the output. Meanwhile, transaction 1 will then read B and complete the financial transaction. It will give the $50 it took from A to B. It'll write B and unlock it. Now observe a problem here. We just lost, T2 just thinks that we lost $50 because it read an intermediate value of A, 950, but then it read B. Then it read B before A got the chance to update B accordingly. So that's a problem. We've just lost $50 here that we weren't supposed to. More to the point, you can't really say there's a serial ordering here. You can't say that to the database it looks as if T2 came before T1 because T2 reads A after T1 writes to it. So you could say, oh, well, what if T1 came before T2? But if T1 came before T2, well, that wouldn't really work either because T2 is reading the value of B before T1 writes to it. So you can't say T1 came before T2, and you can't say T2 came before T1. So this isn't serializable in that case. There's no serial ordering. So this is a problem. But now let's go to two-phase locking. And in two-phase locking here, what's going to happen? T1 is going to lock A with an X lock. It's going to read A. It's going to update A. It's going to write A. Then it's going to acquire a lock on B. Then it has all the locks it needs to complete its transaction. Now we're done operating with A. And so we can unlock A. T2 will acquire a shared lock on A and read A. T1 will then read B, write B, update it by transacting the $50 to B, write it, and then unlock it. And then T2 will get its shared lock on B, unlock A, read B, unlock B, and print the output. And here for T2, it'll actually now get the correct values. It'll actually read and print the correct values. Because it didn't get to, because we, in our acquisition phase, locked A and B before T2 got the chance to get any of those locks. So T2 wasn't able to claim a lock on something that we would need later on if T2 had to come after T1. So it's not going to read, it's not going to read some invalid pair of intermediate values like 950 and 2000, like we did in the non-two-phase locking schedule. That's not going to happen. So here, the ordering you would have would be T1 and then T2, and that would be the serial equivalent of the schedule. Now, in strict two-phase locking, what would happen? In strict two-phase locking, essentially we would first lock A, and then we would lock B. Well, we lock A, read, update, write A, lock B, read, update, write B, and then unlock A and unlock B. Only after that would T2 get to operate on any of the resources A or B. And this would essentially be the strict 2PL implementation of it. One thing I encourage you to do is compare these two schedules, the two-phase locking one and the strict 2PL one, and see how in the 2PL one, the problem of cascading abort still might exist if I was to abort T1 in and around this read B phase, and why that cascading abort problem does not exist in the strict 2PL implementation. So what schedules does strict two-phase locking allow? Well, It allows a smaller subset of conflict serializable ones because strict 2PL avoids cascading aborts. And so it's going to essentially allow a smaller subset here. It's going to allow the intersection of schedules that avoid cascading aborts and schedules that are conflict serializable. Okay, now let's talk a little bit about the lock manager. We've talked a lot about locks already and locking, but we haven't really talked about what, deals with the locks themselves. So let's do that now. So how do we lock data? We're going to lock by a simple convention here. It's all within the DBMS. We're going to observe a lock protocol. If your transaction holds a lock and my transaction requests a conflicting lock, then I am going to be queued up waiting for that lock. Specifically, we're going to have this thing called lock manager, which is going to it's going to handle lock and unlock requests. This lock manager is going to maintain a hash table that is keyed on the names of the objects being locked. It's going to key on your names of your resources, and it's going to keep an entry for each currently held lock. The entry will contain the granted set, which is the set of transactions currently granted access to the lock mode, which is the type of lock held. Is it shared? Is it exclusive? And the wait queue, which is the queue of lock requests. So what happens when a lock request arrives? Well, we're going to see, does any transaction in the granted set or the wait queue want a conflicting lock? If no, we're going to put the requester into the granted set. We're going to grant that lock, and then we're going to let it proceed as normal. But if yes, if there is a transaction in either the granted set or the wait queue that has that wants a conflicting lock, we're going to put the requester into the wait queue and tell it to wait its turn. It has to wait for everything else to go through before it can get the lock it wants. We're going to make a quick exception here, though, which is that if a transaction holds a shared lock and it wants to upgrade to exclusive, we're going to put this request at the front of the queue. We'll see why in a second. Here's the pseudocode for lock management. I'm going to skip past this one largely because it's already in your notes and because really it's just something that if you want, you can take a read through the slides on your own time. It's something it's really just putting into pseudocode what we just talked about in the last 3 minutes of this lecture. For some people, reading this works better than for watching lecture, and I understand that. And if that's the case, I encourage you to look at this. These are also in your course notes. But let's walk through an example of the lock manager. Here's the existing set. Resource A has T1 and T2 holding a shared lock on it. And in the wait queue, we have T3, which wants an X lock on resource A. For resource B, T6 has an X lock on it, and T5 and T7 are queued up waiting to request and get an X lock and an S lock specifically. Now T4 comes along and it says, hey, I want a shared lock on A. So can we grant it? Well, a shared lock on A is compatible with what's in the granted set, but T3 wanted an exclusive lock and T3 is in the wait queue. So this request, T4, shared lock of it on A, that actually conflicts with something in the wait queue. So we would have to put it in the queue. We'd have to put it at the back of the queue. What happens when we release some locks? So let's say T6 releases the exclusive lock on B and T1 releases the shared lock on A. Well, here, what's going to happen is T1 is going to release its shared lock, and here T2 will now have a shared lock. And you might think, well, can we grant T4 now? No, we can't, because T3 of X comes before T4 in the wait queue. T3 wants an X lock, and it requested that X lock before T4 requested its S lock. So when we release T1, we're going to look at the wait queue. We're going to see, Okay, can we grant the first request in the queue? No, we can't. An X lock conflicts directly with an S lock, so we can't give that. So T4 is still going to have to wait its turn. Meanwhile, in resource B, T6 is going to release X of B. Now there's no lock held on resource B, so T5 can get the X lock that it wants on resource B. So we'll remove it from the wait queue and grant the lock. Put it in the granted set. So there's this interesting thing then that you might have noticed where we put T4 in the wait queue, even though it didn't really conflict with anything in the granted set. And you might ask, isn't that a little bit inefficient? Well, it turns out that there is an alternative implementation. I wouldn't say it's better or worse. It's just different. It has different pros and cons, but this alternative implementation is called queue skipping. And it basically says, does any transaction in the granted set want a conflicting lock? You shouldn't consider the wait queue for this, just the granted set. Now, if no transaction in the granted set wants a conflicting lock, we will put the requester into the granted set and let them proceed. If a transaction in the granted set wants a conflicting lock, we're going to put the requester in the wait queue. When a lock is released, we're going to scroll through the queue in order and grant any pending requests that we can. So here's an example. Your existing set here will be on resource A, you'll have T1 and T2 who have a shared lock, and T3 is waiting with an X lock. Now, T4 comes along and it says, I want a shared lock on A. And so you say, well, does that conflict with anything in the granted set? No, it doesn't. So I can grant the shared lock on A. And I'll allow it to bypass the queue. It doesn't matter that T3 wants an X lock here because the granted set doesn't have any conflict. So the granted set is then going to get T4 added to it. T4 will get its S lock. And this is some pseudocode for queue skipping. Once again, this is in your notes, so I'm going to move past it in this lecture. But in case this is the type of thing that you find conducive to your learning to read the pseudocode for it, I strongly encourage you to go and read the notes for it. This isn't really saying anything that we didn't just cover in the last 2 minutes. So if you understood what we talked about in the last 2 minutes, you're good to go. Now let's bring up an example here to segue into the next part of our lecture. Let's say that I was going to lock, T1 is going to get an X lock on A, and then T2 gets an S lock on B. T2 then reads B, and then T2 wants an S lock on A. And so T2 says, okay, well, I have to wait for T1 now. Meanwhile, T1 goes about its business. It reads A, it updates A, it writes A, and then it's going to try to get an X lock on B. Now, here's what the lock table looks like. For resource A, T1 has an X lock, and T2 is in the wait queue. It wants a shared lock. For resource B, T2 is going to hold a shared lock, and T1 is going to want an X lock, and that's going to be in the wait queue. And now we have a problem because T1 and T2 are waiting for each other. This is called a deadlock. So let's talk about that. A deadlock is a cycle of transactions waiting for locks to be released by each other. And there are 3 ways of dealing with them: prevention, avoidance, or detection and resolution. Now, many systems might just punt and use timeouts, but there are some dangers with this approach. So first, let's talk a little bit about prevention. So let's go through some ways we can deal with them instead. Let's talk first about prevention. Okay. And before I talk about prevention, perhaps it's best that I deal with the scenarios themselves so we know really what we're going through. Specifically, when would deadlocks occur? And why is it so important that we learn how to deal with them? Well, sometimes they're just unavoidable. For example, in the first case, T1 has an S lock and T2 wants an X lock on A, and then T2 has an X lock and T1 wants an S lock on B. Well, structure here means it's just unavoidable. I can't really figure out a way to block that from happening. So very commonly, something like this is going to happen. Now, we could also have just a bad implementation of the lock manager itself, the lock upgrade, which is entirely avoidable if we prioritized upgrades. If you were wondering why we made that wrinkle in our rules earlier on to prioritize lock upgrades, this is exactly why. Because here you might see T2 wants an upgrade to the lock that it holds. And so it's going to look and it's going to see, oh, well, T3 wants an X lock and T4 wants an X lock, so I'll have to wait for them. But then T2 is blocked. It's waiting. It's not going to release its locks until it's done. So what's going to happen now? Well, T3 and T4 are waiting for T2 to release its S lock, and T2 isn't going to release its S lock because it's blocked, waiting for T3 and T4. So that's a case in which you would just get a deadlock. Now, that's entirely avoidable if you prioritize upgrades. And that's why we made that wrinkle in our rule. One of the other cases in which you could have it is if you have multiple transactions that want to upgrade their locks. This is also unavoidable. For example, here, even if we prioritize upgrades, T1 and T2 both want to promote to an X lock on resource A. Well, now they're both kind of waiting for each other, and neither of them is obviously going to cede because they're both trying to get the same X lock on resource A, and they both hold S locks already. So here, very clearly, they're going to be stuck in a holding pattern, and there's again a deadlock because they're both waiting for each other. These are some scenarios for deadlock. Now let's talk first about prevention. This is a common technique in operating systems where the standard approach would be resource ordering. For example, you would first prioritize the screen to the network card to the printer, but this isn't really feasible for transactions in a database management system because you can't really order files or tuples in the same way you would order resources. You can't give priorities, for example, to file 1 versus file 2 in the same way you could give a higher priority to a screen versus a network card. So here we're going to have to deal with something different. We're going to assign priorities to transactions based on age. So let's say that T sub I wants a lock that T sub j holds. Now there's two possible policies here. Number one is wait die. If T sub I has a higher priority, if it's older than T sub j, then T sub I will wait for T sub j, else T sub I will abort. The second possible policy is wound wait, which is basically if T sub I has a higher priority, then T sub j is going to abort, else T sub I will wait. The way to think about this, because this is really kind of confusing to remember, is it's like what happens if the transaction is older and it wants a lock that something else holds versus what happens when the transaction is younger and it wants a lock that something else holds. The older transaction in wait die will wait. The younger transaction, if it's the younger transaction and it wants a lock that something else holds, that an older transaction holds, it'll die. In wound wait, if it's an older transaction and it wants a lock that a younger transaction holds, it's going to wound the younger transaction. It's going to kill the younger transaction. We're going to abort the younger transaction. We're going to give that lock that younger transaction held to the older transaction. Otherwise, if it's the younger transaction that wants a lock that the older transaction has, we'll tell the younger transaction to wait its turn. And these diagrams are actually very helpful. They're quite cartoonish, but they're quite, not only are they quite funny though, they're actually very, very useful in helping remember exactly what wait die and wound wait is. The old person here is like an old transaction, and the upright person here is like the young transaction. And you can kind of see what happens in each of these cases. So be familiar with both wound weight and weight die. So these schemes guarantee no deadlocks because in the previous images, we're going to actually just abort the younger transaction if the, in weight die, say, we're going to abort the younger transaction if it's waiting for an older transaction. Or in wound weight, we're going to abort the younger transaction if it holds a lock that the older transaction wants. So here, because we're like essentially like shooting one of the transactions, we're not going to end up in a cycle here. There's not going to be a holding pattern. But there's an important detail here. If a transaction restarts, if we do actually kill the transaction to make it restart, we need to make sure it gets its original timestamp. It gets its original priority. So it doesn't become younger. It doesn't get a new timestamp based on when it respawns. Because if we did that, if we didn't give it its original timestamp, then the transaction would always be the youngest one, and then it would keep getting aborted. And that's not good. At some point, we want to complete that transaction. So we're going to give it its original timestamp. Now, you may have had other priority schemes that you could use. For example, the number of locks acquired, like which is a measure of resource consumption. That's valid. We're going to talk about timestamps here, but you could use some of those other resources, some of those priority schemes too. Now, what's the problem with the deadlock avoidance algorithm? Well, concretely speaking, there are a lot of aborts. So maybe something more efficient would be to just detect when deadlocks happen and abort when needed. And what we're going to do for that is we're going to maintain this graph called a waits for graph. What that waits for graph will show is if a transaction cannot acquire the lock because it is held by another resource, we're going to draw an edge from that transaction to all the transactions currently holding conflicting locks on that resource. We'll go through an example of that in a second if this doesn't really make any sense right now. We're going to check for cycles in that graph. And when there's a cycle in the graph, it means that, a set of transactions are all waiting for each other. So there's a deadlock. Let's walk through an example. T1 is going to ask for a shared lock on A. Then it gets a shared lock on D. And then T2 comes along and it gets an X lock on B. So far, so good. Now T1 says, oh, I wanted a shared lock on B. And T2 says, well, tough, I have that. So T1 is going to wait for T2. So there's an edge going from T1 to T2. T3 comes along, gets a shared lock on D. That's fine. Nothing bad here. It gets a shared lock on C. That's fine. And then T2 says, I want an X lock on C. And so it has to wait for T3 because T3 has a shared lock on C. So we're going to draw an edge from T2 to T3. Then T4 comes along and T4 says, hey, I want an X lock on B. Now we say, well, you can't really do that because T2 has an X lock on B. So we're going to draw an edge from T4 to T2. Now notice something here. There's no edge from T4 to T1, even though you might see here that T1 was going to make a request for a shared lock on B before T4 came along. But in waits for graphs, we only draw arrows based on what holds a conflicting lock. The only transaction here holding a conflicting lock is T2. So you're going to draw a T4 to T2 edge. And this is a key difference between the waits for and the dependency graph. In the dependency graph, for example, you might have seen that we have to draw an arrow from any pair of conflicting operations. That's not going to happen here because here we're only going to draw an arrow from one transaction to another if that transaction is waiting for a lock on a resource and the transaction we're drawing the edge to, in this case T2, has a conflicting lock that it's holding. Now proceeding with our example, T3 comes along and it wants an X lock on A. And so T3 says, All right, well, I'm going to have to wait for T1 because T1 has a shared lock on A. And now we have a cycle. T3 is waiting for T1, which is waiting for T2, which is waiting for T3. So this is a deadlock. And so T1, T2, T3 are going to be involved in a deadlock. T4 won't be involved in it, to be clear. It's just T1, T2, T3. Those are the three in the cycle. So in the background, what we do is we're going to run a deadlock detection algorithm, going to build and periodically extract the weights for a graph. We're going to find the cycles in that graph and then shoot a transaction on the cycle. Empirically, most deadlock cycles are small, so this isn't nearly as tough to build as one might think. Now, I want to have a brief aside of conflict dependency graphs versus wait for graphs. In conflict dependency graphs, which is what we covered last lecture, you may remember that you drew an edge from one transaction, T sub I, to another T sub j, if and only if T sub j and T sub I were working on the same resource, and at least one of T sub I and T sub j was a write, and T sub I came before T sub j. Weights for graphs, you're going to draw an edge from one transaction, T sub I, to another, T sub j, if and only if T sub j holds a conflicting lock on the resource that T sub I wants to operate on, meaning that T sub I must wait for T sub j. This is used for deadlock avoidance. So be very careful. These are not the same. One is not the inverse of another. If you want an example, you can revisit our part 10 of the graph example we just did. You know, if you were following the rules for dependency graphs, but inverting them, you might have been tempted to draw an arrow from T4 to T1. That's not correct. Don't do that. Only in weights for graphs, you only draw an arrow from a transaction to whatever transaction holds conflicting locks currently on that resource. Okay, now let's wrap this lecture up by talking a little bit about locking granularity. Now let's talk about locking granularity. Up until this point, we've said a lot about locks and deadlocks and all of that good stuff, but we haven't actually talked about where those locks are placed and what they're placed on. I say resource A, but what is resource A? So it's hard to decide what granularity to lock. Are we going to lock tuples? Are we going to lock pages? Are we going to lock tables? And when we make that decision, we have to figure out, right, what are we sacrificing? What are we gaining? Fine-grained availability of resources would be nice. For example, if transaction placed locks on each tuple, well, that would be cool because, you know, we could get very high levels of concurrency. But then having a small number of locks to manage would also be good. For example, a lock per table. We can't have both, right? Or can we? So one thing people realized early on, specifically Jim Gray, was that you shouldn't have to make the same decision of granularity for all transactions. That is, different transactions should be able to lock at different granularities. So in order to do this, we could define a hierarchy of data granularities. The small, like the tuples, are nested within larger things like pages and tables and the database itself. This can be represented graphically as a tree like this. And the levels would be from the coarsest to the finest are database, tables, pages, and records. And when a transaction locks a node in the tree explicitly, it's going to implicitly lock all of the node's descendants. So if I placed a shared lock on T1, then I would also implicitly have a shared lock on P sub B, on R sub B1, and R sub BK. And those locks would be implicit, and the explicit lock would be on T1, the shared lock. So now we're able to lock different levels of the tree depending on the access patterns of our transaction. Lower on the tree with fine granularity, we can lock individual tuples, and that'll give us high concurrency, but we'll have a lot of locks. Coarse granularity, which is higher up in the tree, means fewer locks, so there's less overhead, but you're going to lose some concurrency. So you really want to choose now whether or not to go for the fine or the coarse granularity based on the access patterns of your transaction specifically. Am I going to be modifying, for example, the whole page? Am I going to be modifying just a single tuple? These are decisions that we would need to make now and that are enabled by multi-granularity locking, where I can then place the lock at different levels of the tree based on what my transaction's access patterns are. So these are some real world locking granularities. For example, the RID, the key, the page, these are all the lower levels. And then you could see the upper levels, which is like the table, the file, the application, the database. And this is from Microsoft SQL Server. So you can see this vast hierarchy of data and the different levels at which you could place your locks. Now, the key thing behind the idea of multi-granularity locking will be this thing called intent locks. Intent locks will allow the transactions to lock at each level, but with a special protocol. Basically, before getting your S or your X lock, the transaction needs to have the proper intent locks on all of its ancestors in the granularity hierarchy. For example, if I wanted a shared lock on piece of B, I would need an intent to share lock on T1, its ancestor, and then I would need an intent to share lock on the database itself. Basically saying that I intend to put a shared lock later on down the line in this tree, and then I would follow the chain of intent locks until I actually have my shared lock itself that I want to place. Why is this useful? Well, think about it like this. I don't want to put an S lock on the database itself. That would be ridiculous. I would block off a whole bunch of transactions from doing a lot of useful and important things just because I wanted to read from one page. So we don't want to do that. At some point, though, we do want to make sure that no other transaction can walk around and say, oh, hey, I'm going to put an X lock on that database because you're reading a page from there. So you need to put some lock here to indicate that you're reading something later on down the tree. But what is it? So that's where intent locks come in. And we'll basically say the purpose of the intent lock is to signal to other transactions that you're going to be operating on something later on down the tree. And that will help them, and that'll help you essentially avoid locks getting placed that could cause conflicts. For example, no transaction can now put an X lock on the database because you've said, I'm reading something later on down. You don't get to just X lock the database because I've already claimed part of this for myself. So I'll put an intent to share lock here, an intent to share lock here, and a shared lock here. There's 3 additional lock modes that we're going to introduce. Number 1 is IS, intent to get S locks at finer granularity. Number 2 is IX, an intent to get an X lock at the finer granularity. And number 3 is a 6 lock, which is like S and IX at the same time. You might ask why this is useful. One thing that I would encourage to think about is like a SQL update statement. In the SQL update statement, for example, if you're going to update a row there, you might want to first read let's say, well, let me give a concrete example. Let's say I'm going to update the ratings from sailors where the sailor's name is Bob. So I'm going to have to search through all the sailors' names to find Bob. And I'm going to have to update their ratings. So I would need to place an X lock on certain records and certain tuples. But I would need an S lock on the entire table because I need to search through the entire table. So I have an S and then need to put an IX lock on the table, signifying that I'm going to write to some small components of this table. Intent locks allow a higher level node to basically be locked in S or in X mode without having to check all of its descendants. So let's talk a little bit about the locking protocol. Every transaction is going to start from the root of the hierarchy. And to get an S or an IS lock on a node, you need to hold the IS or the IX on the parent node. To get an X or an IX or a 6 lock on a node, SIX, you need to hold an IX or an SIX lock on a parent node. I say 6 for shorthand. You can say SIX or 6. It doesn't really matter. As long as you know that SIX means shared intent exclusive, that's what really matters. Now, you need to release your locks in a bottom-up order. So from the finest granularity upwards. We're going to enforce two-phase and lock compatibility matrix rules in this process as well. And this protocol essentially is equivalent to directly setting locks at leaf levels of the hierarchy. What do I mean when I say lock compatibility matrix? What is that even talking about? Well, recall that I said, you might remember back here, I had said something about, what I would do if someone wanted an X lock here. We'd say, hey, that's not allowed because I have, an intent to share lock here, which signifies that I'm reading something later on down the tree. So clearly I can't, no other transaction then can then come along and put an X lock on the database because that would conflict with the IS node. It conflicts with the purpose of what that's trying to signal. And so we can extrapolate that idea. We can basically say, what two locks are allowed on any given resource from two different transactions. A simple case to remember, if you can follow my cursor right here, is when can two intent locks be compatible? Well, it's when the locks that they actually refer to, the explicit locks that they're going to refer to, like the S or the X locks, when they are compatible as well. So for example, here in this case, is this a scenario that can exist? Can I have an S lock on the tuple T1 and an X lock on the tuple T2? Yes, I can, because they're not on the same resource. They're on two different ones. On two different resources, it's completely fine if I have an S lock on one and an X lock on another. There's no conflict there. So in their parent, in their ancestor, it's okay for that ancestor to have IS from one transaction and an IX from another. That's completely fine. That's allowed. And that's something to basically remember here. You might wonder, well, hey, isn't it possible then that you could theoretically be opening the door for an S lock and an X lock to be placed on the same resource then, if you have an IS and an IX on the same resource? The answer to that is we typically let conflicts get resolved lower on down the tree at that level itself. We don't worry about it at the intent level. The intent levels basically are pretty simple. You're going to allow things like IS and IX to be together. If you can think of a case where the two intent locks can be compatible, or the resulting scenario from the two intent locks, such as an S lock on T1 and an X lock on tuple T2, would be present and compatible later on down the tree. And if you extrapolated that principle, if you extrapolated the lock compatibility matrix principle, you would basically get something like this. So I would strongly recommend copying this down and putting it on your cheat sheet. You will need to have very, very strong familiarity with this for any exam that we'll have in this class. You will also need to know this very well for the project that you're going to be about to do. So I would strongly recommend getting familiar with how different locks are compatible and why they're so. For example, an IX lock, two transactions could have an IX lock on one resource, like a page, because, well, later on down the line, it could just be the case that, transaction 1, for example, locks tuple T1 and transaction 2 has an X lock on tuple T2. So their ancestor could have an IX from each transaction on it, and that would be totally fine. Two transactions could have an IX on the same page. So construct cases like that, I would strongly recommend, and see where they are and aren't compatible. You may notice, for example, that a 6 lock is not compatible with an IX lock. One transaction can have an IX lock if another transaction has a 6 lock on the same resource. Why is that? Because a 6 lock basically means that you have a shared lock on the resource and its subtrees, its descendants, as well as an IX lock on that node. And so an IX lock from another transaction would basically mean that other transaction says, hey, I'm going to write lower on down the line. For example, if I have a 6 lock on the table and another transaction comes along and says, I want an IX lock on this table. Well, then it would basically be saying, I want to write to something that you already have a read lock on. So it would be trying to place an X lock later on down the line. And that's not possible because I've implicitly given an S lock to the pages and the tuple. So that's not allowed. That's why a 6 lock and an IX lock wouldn't be compatible on the same node. So I would strongly encourage you to work out exercises like these and see if you can fill in the lock compatibility matrix yourself. Real-world lock compatibility matrix can get extremely complicated. This is what they would look like from Microsoft SQL Server. You can see an incredible amount of locks here. We won't be covering that in this class. You should just be familiar with these 5 locks: IS, IX, S, SIX, and X. If you're familiar with that, you'll be fine for this class. And so we talked about serializability, and we talked about conflict serializability, and we talked about how two-phase locking and strict two-phase locking are going to implement these notions of conflict directly. We also talked about deadlocks and how to keep tracks to the locks issued. And we talked about multi-granularity locking and how you can lock different levels of the system, different levels of the database, according to the access patterns of your transactions. And that allows a nice trade-off between the scope of the locks and the number of lock entries in the lock table. There's a lot more to this story, but for the purposes of your project and for the purposes of this class, this should probably be a pretty good start and basically the extent of what we're going to cover regarding locks themselves. There are some excellent resources on this as well, including the notes, the discussion slides. I strongly encourage you to do whatever is necessary to understand this topic very deeply, because it will show up again and again, both on exams and on your projects. Thanks for watching, everyone. Have a great day. I'll see you all Wednesday.